All right. Let's see. All right. Thanks, everyone, for joining. Tonight's a movie night where RocDev reacts to advanced design patterns for DynamoDB. If anybody has any questions, shout them out. I'll try to hit pause as quickly as I can, and we can talk about it. At various points, I might do that myself just to say, "Ooh, that looks cool." Who knows? It's an experiment. We'll see how it goes. And if there are no other comments before we get started, I'll just go ahead and hit play.
I do a lot of DynamoDB work, although I work across technology stacks. I do a lot of MongoDB and Cassandra as well. Most of the design patterns I'm going to be talking to you about today actually apply to all NoSQL databases. They're going to be presented in the form of a wide column key value store, which is what DynamoDB is. If anyone's interested in figuring out how to apply those design patterns to MongoDB, track me down after the session. I'll show you how to do this in the document store as well. But I do this a lot, and one of the big messages I like people to take away is there's really not a lot of difference between the various technology platforms. The design patterns pretty much apply across the board. So what we're going to talk about today, I always like to talk about a brief history of data processing to kind of set the tone, the mindset for why are we even looking at NoSQL. And it's pretty important that we understand this because we've had this great technology for many decades, this relational database that seems to do everything. So why would I spend my time learning this new technology, which is seems to be so alien compared to what I know already. We'll talk a little bit about that. We'll get into an overview of DynamoDB. I'm not going to spend a lot of time on this. This is a 300 level session, so it's going to be a very brief overview of the NoSQL service offering we call DynamoDB. And then we'll get really into the meat of the discussion today. Is going to be about NoSQL data modeling, and we'll talk about normalized versus denormalized schema and what that really means. How do we build data structures into a NoSQL database like DynamoDB? And then I'm going to get into some of the common design patterns. Now, historically, or throughout the last couple of years, I've really focused on base use case design patterns. But this time, we're really going to go deep into relational modeling. I'm going to focus on composite key structures. For the most part, we'll talk about how to translate hierarchical data models, how to translate relational data models into NoSQL. So this is really going to be representative of a lot of the work that my team does, which has been working with global strategic accounts as well as our internal Amazon retail teams to migrate from relational database application services into NoSQL databases. And we'll close out with a real quick discussion about serverless and talk some about modeling real applications. And I'll give you an example of a real Amazon service that we did with very complex and a long list of access patterns. So again, first thing I like to talk about is the history of data processing. And I love this quote. I don't know who said it, but listen to and look at what happened in the past so that we don't repeat the mistakes of the past. And that's a lot of what this message is about. So if you look at the timeline of database technology, it's really comes down to a series of what I call peaks and valleys in data pressure. And data pressure is the ability of the system to process the amount of data that I'm asking it to process in a reasonable cost or a reasonable time. When one of those dimensions is broken, that's a technology trigger, and we invent things. And we've done a lot of that invention over the years. So the first database we had was a really good one. We're all born with it. Stuck between your ears, highly available, right? When my eyes are open, it's online, but maybe questionable durability, about zero fault tolerance. It's a single user system. So pretty soon we figured out that we actually need to do something better than that, and so we started writing things down. And we developed a system of ledger accounting, which is our first structured data store that we had. And that ran public and private sector applications for several millennia until 1880 US Census came along, and a guy named Herman Hollerith was tasked with collating and processing all of the data that was collected. Now, if you're familiar with the US Census, it runs every 10 years, and it took Mr. Hollerith and his team about 8 of those 10 years to process that data in 1880, and he figured out he needed to do something different. So he invented the machine-readable punch card and the punch card sorting machine, and the era of modern data processing was born, as well as a small little company called IBM, which has a large and long and storied history on database technology. So rapidly we developed many technologies as public and private sector applications started to consume these new technologies and produce applications that required more and more and more data. So paper tape, magnetic tape, faith. Distributed block storage, random access file systems, and along came 1970 or so, the relational database. And it's important to understand why we built the relational database. And we did it because storage was expensive, extremely expensive. In the mid-'80s, I was at Macworld in Moscone Center in San Francisco. I was walking through the convention center, and I saw in the middle of the conference room floor there was a truck transmission. And I was like, why is there a truck transmission in the middle? Maybe there was an RV show or something, and they couldn't get it out of there. And I walked over to look at it, and really it wasn't a truck transmission, it was a hard drive from 1974. And it was cross-section, it was really cool looking. But it had a sticker on it that said 4 megabytes and MSRP $250,000. Right? That's pretty expensive. And now obviously we didn't use a lot of magnetic disk in 1974, but the point is that storage was extremely expensive. So normalizing the data, right? Reducing the footprint of that data on disk was extremely important, and that's what we did. The relational data store is a wonderful way to reduce the storage cost of your application, and what does it do? It increases the CPU costs, because the complex queries it must execute to produce the denormalized views of data that your application consumes, right? Joining tables. It's extremely expensive. So now fast forward 30, 40 years.
Quick interjection there. It seems like his argument so far is that cost of the drive of the storage is solely, maybe primarily the reason for relational databases. But I would also think there's a cost of data duplication in that I update one record and not the other.
Yeah,
right?
Data integrity is a huge thing, right? Otherwise, we wouldn't have foreign keys.
Right.
Yeah, the integrity and consistency of the data it seems like he's skipping over like the most important aspect of relational normalization. So
now there's probably, I mean, cost. I will say that if $250,000 was much more than a single person's salary at that time, probably 5 times their salary, more than that. So it might have been the primary reason and why the CEOs cared.
It might have been why it was invented, but by far and large, I think the majority of people that use it still today, it's for data integrity, knowing that every record has the same fields and or, you know, foreign keys and things like that.
Yeah, I think that's a good TLDR, right? It was invented possibly because of cost, but it's survived because of the other reasons that we mentioned.
Yeah, transaction management would be the other one, right? Atomic operations.
Right, ACID, yeah.
Yep.
Exactly.
All right. Well, I guess let's keep going.
The most expensive resource in the data center is actually the CPU, right? It's not the storage. So why would I want to use a technology that's optimizing the least expensive resource in the data center? And this is really why we're looking at NoSQL today, right? Because we want to do things more cost effectively and more easier on the wallet, so to speak. So when we use new technologies, it's important to understand how to use them before we use them. And most of the teams that I work with actually kind of fail this test. They kind of take their relational design patterns, they deploy multi-tables, implementations, normalized data models in NoSQL, and then they wonder why is it not working? It's so terrible, and it's really due to this effect. So if you look at the bottom, this is the technology adoption curve. We're all very familiar with this. In the beginning, we have innovators running around solving a problem. A technology trigger has occurred, right? The data pressure is too high in the system. We need something that's going to be able to process this data a little bit more efficiently. They land on a solution. In this case, we're talking about NoSQL technology. The few people have some really good results, and the rest of the market starts to move there. And as people start to deploy the new technology, they realize it doesn't work, right? Not for them. Their use case is different. The other people must be doing something or have a different application. The reality is no, you're probably just using the technology the same way you use the old technology, and typically new technology doesn't work the same way. So if you actually learn how to use it first, you'll have a better result. And so if you look at the bottom chart, the relational technology, that's way out on the right-hand side, the laggards, right? If you don't understand what a join is today, then you've been living in a cave for 30 years and I can't help you, right? But if you don't know how to build a denormalized data model, well, that's fully understandable because NoSQL technology is over on the left-hand side, right? That's where the innovators are still operating. We're still in that technology gap. People are still trying to understand this new technology. So if you take the time to actually learn how to model your data correctly in a NoSQL database, you're going to have a much better result. And so that's what we're going to talk about today. How do I actually model the data? Before we get there, it's important to understand that this relational database that we've been using for 30 or 40 years, well, it still has a very good place in the modern application development environment. And that really comes down to what types of access patterns are we trying to deal with this application service. Are they well known and well understood? Then maybe that's a perfect database or a perfect application for a NoSQL database, right? Where I have to actually structure the data specifically to support the given access pattern, and that's how come NoSQL databases can be more efficient. But if I have the need to support ad hoc queries, right, it may be a BI analytics use case, an OLAP style application, that might not be the best application for NoSQL because NoSQL databases aren't really good at reshaping the data, right? They like simple queries, select star from. They don't like complex queries, inner joins and calculate values and these types of things. NoSQL databases are not very good at that. So that's what it really breaks down to. The OLTP application is an excellent application for NoSQL databases, and good for us. That's 90% of the applications we build because they represent very common business processes. Right? When I go to Amazon.com and I order, and I hit the order button, the same thing happens every time, and that's really the crux of when is it a good decision to use a NoSQL database. If I understand the access patterns very well, they're repeatable, they're consistent, then that's when we go to NoSQL. If not, then let's look at the SQL database, right? So it's not obsolete, and it's just now we have a different choice. The Amazon DynamoDB is a fully managed NoSQL database. How many people in the room have actually run NoSQL databases at scale? I'm talking like 50 or more nodes. Yeah, not very many. When you get there, you will realize that managed services are really cool. And most of the customers I work with have scaled out their Cassandra clusters, they've scaled out their MongoDB clusters, and oftentimes I'll work with them to kind of correct whatever mistakes they've made in their data models to get a little bit more life out of that cluster. But sooner or later, they're going to say, it's too expensive. It's hard to run this. I don't want to manage it anymore. I have a 724 NOC that I'm staffing 365 days a year to manage all of this infrastructure. Whether it's running on EC2 or on-prem, it's irrelevant. It's the same cost. Right? Server updates, patching operating systems and software, rebuilding storage devices, failed nodes, all these things. Nobody wants to do this. That's not core to your business. So the fully managed aspect of NoSQL database services is really the most powerful feature that you can have. It's a document or key value store. What we really mean is it's kind of a wide column key value store that supports a document attribute type. We'll talk a little bit about that later on. And really scales to any workload, is fast and consistent at any scale. DynamoDB has single tables running upwards of 4 million transactions per second with low single-digit millisecond latency. As a matter of fact, one of the most interesting characteristics of DynamoDB is the busier it gets, the more consistent the low latency responses become, and that's because we have a fully distributed request router, and as you start to hammer the request router tier more and more, the partition information of your NoSQL table starts to get cached across the front end. So there's no more lookups on that configuration table. So if you look at services like Snapchat, when the White Sox won the World Series, they were peaking out at 3.5 million transactions per second or so, and the graph is just really interesting because the latency drops to a very flat, low 1 to 3 millisecond range as they approach their peak. And fully fine-grained access control. In DynamoDB, we can restrict the access to the items on the table itself, and to the attributes within the item. So if I have an application process that's running against a data store that might have items that contain information I don't want to have visible to my order entry clerks, but maybe they have annotated data that's interesting, like maybe sales person's commission data and whatnot, that I want to have access to sales managers, I can have those access patterns hit the table with different IAM security permissions, which gives me a fine-grained access control over the data and what people can read. And then it's a backplane service, which is really great when you talk about serverless programming, and we're going to talk about that at the end of this. And why is that really a big value to customers today? So DynamoDB has tables like all databases. A table in DynamoDB is more like a catalog in a relational database. You're going to put many, many items into the table. And the items in the table don't always have to have the same attributes. But they do have to have one attribute that uniquely identifies the item, and that's the partition key. So every attribute I insert into a DynamoDB table must at least have a partition key attribute. I can also include an optional sort key attribute, and when I do this, it gives me the ability to execute complex range queries against the items that are in those partitions. So you can think of the partition as now a folder or a bucket that contains items, and the sort key orders the items within that folder. And so when I query those partitions or those folders, I can execute those queries with complex range operators. So in this example, let's say I have a partition key might be a customer ID, and the sort key might be the order date. And I want the customer, and the primary access pattern in the application is give me all of the customer's orders in the last 24 hours. So I could say query the table where the partition key equals customer ID X, and the sort key is greater than 24 hours ago. That gives me a nice filtered list of orders by customer over the last 24 hours. So that's a really good way to maintain that one-to-many relationship. And you typically want to model the table to support one of your primary access patterns. When we get into the actual data modeling, you'll see what I mean by that. You always want that table to be able to query something that is interesting to the application. Partition keys are used to uniquely identify the item. They're also used to distribute the items across the key space. So every table in DynamoDB represents a unique logical key space, and we're going to distribute those items by taking that partition key attribute and creating an unordered hash index and laying these items out across this virtual key space. This is the way all NoSQL databases actually work, and when we scale the database, we're just going to chop that key space up and spread those items out across multiple physical storage devices. So now when I query the system, I'm going to always provide that partition key as that equality condition, so the system knows exactly which storage node to get to go read that data. This is what makes all NoSQL databases fast and consistent at any scale. There's automatic routing of the query to the exact storage node that needs to be served to service the request. When I include the range key or the sort key in the table schema, now when I query and I provide that sort key condition, I'm going to go into the partition, selectively read the items that are co-located on the same storage node and sorted using that sort key attribute. And this is, again, this is how NoSQL databases maintain that fast, consistent behavior. This is not unique to DynamoDB. All NoSQL databases have this construct. Partitions in DynamoDB are automatically three-way replicated. So when I write to DynamoDB, you're going to get an acknowledgement from the client when two of the replicas have received that write. When you read from DynamoDB, then you have a choice between eventual consistent and strongly consistent reads. Typically, it's up to you how to do that. We recommend that you use the eventual consistent read because that three-way replication, the primary node to secondary is sub 1 millisecond. So you're not all that eventually consistent. It's pretty much by the time you round trip back from the client, the data is going to have replicated the secondaries. Eventually consistent reads are half the cost of a strongly consistent read because we have more nodes to choose from. When you make that eventually consistent read, I'm going to randomly read from one of those three partitions. If you make a strongly consistent read, I'm going to read from the primary node. Primary node always accepts the write, so you're going to get a very consistent read, on guaranteed strongly consistent read off of the primary, but it is twice the cost. So a cheap way to double the capacity of your application is to use EC reads. They are on by default, so unless you change that parameter, that's what's going to happen. Local secondary indexes, well, we have two types of indexes in DynamoDB. We have local secondary indexes and we have global secondary indexes. Local secondary indexes allow you to resort the data in the partitions, right? So let's say in this case, I have a need to get all the back-ordered items for a customer. My primary use case is in the primary table, say order ID is the partition key, sort key is the date, but on my GSI or my LSI, I'm going to create a partition key which is the same as the table, which it must be, which is the customer ID, and then I'm going to resort the data using maybe order state, right? So now I can query the LSI and say, give me all the back-ordered items for a customer. and I can query the table and say, give me all the orders for a customer within the last 24 hours, right? So it's a different access pattern. I'm going to resort the data to support that access pattern, but local secondary indexes must always use the same partition key as the table. So it's a way to resort the data, but not regroup the data. The alternative is to use a GSI, or global secondary index, and global secondary indexes allow me to create a completely new aggregation of the data. So in the primary table, which might group the orders by customer, maybe my global secondary index groups the orders by warehouse. And I could say that my partition key on the global secondary index would be warehouse ID, and the sort key would be order date. Now, if I need to get the orders for a given warehouse in the last hour, I can query the GSI by warehouse ID, and with a sort key operator saying greater than 1 hour ago. That would give me everything for a given warehouse in the last hour. So you're getting the idea. What we're going to end up doing as we model the data is we're going to start to use these indexes to regroup, resort, reaggregate the data to support secondary access patterns, right? But using the same types of key structures. So it'll be interesting when we get into the modeling, we'll see some real world examples of how this works. GSI updates are eventually consistent. LSIs are strongly consistent. So it's something to remember when you're working with these. GSIs can, when you make the update to the GSI, you're going to get the acknowledgement back to the client. Asynchronous process will kick off to update the global secondary indexes. Very important to know that the GSIs have to have enough capacity allocated, or the table could end up getting throttled, because we need to maintain the consistency between the indexes and the table. So if you're writing data into the table faster than the GSIs can replicate, eventually they're going to back up. There's a small buffer between the GSI and the table, but if that buffer overruns, we're going to shut down writes to the table until the GSI can actually catch up. So important to know that your provisioning on the GSIs must match the throughput of the table. All right, scaling NoSQL. Technology does work, you just have to know how it works. But I like Douglas Adams, so I put this quote up there. But this is what bad NoSQL looks like. And this is what usually happens when people kind of don't understand how to use the new technology. If you look at this as a heat map, we'll run this for customers. I don't necessarily need to see this. I can look at a table's CloudWatch and say, okay, you're throttling and you're well below your provision capacity. That probably means you have a hot key. In this particular case, we have partition count on the y-axis. We have time on the x-axis. And you can see by that big red line, all of our access is hitting a single storage node. So remember I said key space. We chopped up that key space. In this example, we have 16 different partitions, but something in the application layer is causing a high velocity access pattern to a small number of keys or a single key, and it's causing one storage node to light up. And that is an anti-pattern in NoSQL, in all NoSQL databases. We can force this condition in Cassandra, MongoDB, DynamoDB, it doesn't matter. We want to distribute the access patterns, right? This is what NoSQL is about, is a fully distributed database. So getting the most out of Amazon DynamoDB throughput, it's oftentimes about using partition key elements with large number of distinct values, right? High cardinality sets. We don't want binary partition keys, right? True or false, in or out. These are bad partition keys because it's going to allocate, so it's going to aggregate so much of the data into a small number of partitions. What we really want are things like UUIDs, right? We want large numbers of distinct values, and we want to access those values evenly over time.
Don't use dates as your partition key. I've seen that. Don't do that. It doesn't end well.
How do the indexes work very well if you're using dates?
Well, it's just hashing the partition key, right? So I mean, it's just a string. But if you're using dates, you're probably accessing the most recent stuff and not stuff from,
from older, right?
Right. So
you're still lighting up just one area, or
right.
The last 30 days at all times. Yeah.
It's a horrible. You're switching which is your hot key, but it's not. Yeah, it's not good. Don't do that.
Yeah.
But I've seen people do it, so I'm just gonna highlight that. They're very different. They're very high cardinality, right? Time is infinite, seemingly. It always changes. It's always going forward. And it's very bad to use here. Anyway.
Let's get all of our customers to line up and take a number, right? so we can get them to come in a nice orderly fashion. We all know that doesn't happen, right? There's thundering herds, all kinds of high demand access patterns. But if we can get that data spread out and get those requests arrive more evenly spaced over time, and oftentimes this is about distributing the data, we'll have a much better picture when we look at that heat map. In this particular example, I would probably tell this customer to deprovision the table because it's not really doing too much. It's very much underutilized. I usually like to see a little bit more color. I just like to see things evenly distributed across that key space. I don't see those big red lines. We want pepperoni pizzas on these heat charts, right? So, one thing to mention when we get into DynamoDB is the biggest value, one of the biggest values of Dynamo is the elasticity, right? When I manage a NoSQL cluster like a MongoDB or Cassandra, I have to provision it for peak load. And it doesn't go away because I can't take those shards away. I can't take those nodes off of the ring. I have to actually continue to replicate data and run those and manage that infrastructure whether or not it's doing something. With DynamoDB, we give you a really neat technology to deal with the elastic demand of your application. This is a real application service that runs in one of our fulfillment centers. You can see, like before, without auto-scaling, there was this high bar of provision throughput. Everything under that red line and above the blue curve is wasted dollars. Now with auto-scaling, what happens is as the demand for your application increases and flows and ebbs, you'll see the auto-scaling adjust the capacity on demand to meet the application's access requirements. So this is a really good way to manage the cost of your database. Now, NoSQL databases in general can't do this, so these managed services are really valuable. A managed service like DynamoDB is really valuable because it provides the elasticity, which is a huge cost savings over time. In the middle of the night, when your application is not doing anything, you don't really want to be paying for all of those server instances to be running, and so that's one of the nice things about Dynamo.
One thing to note on that chart, it's almost like too convenient that the auto-scaling red line there is always it's fully it's an envelope of all of the blue access lines. Blue never exceeds the red line anywhere on this chart, and that almost feels...
It's marketing.
Yeah.
Yeah, one thing that I wanted to mention is we've had experience that basically we've had issues where DynamoDB is the thing we're waiting to scale. So this, like it never looks like this. It usually looks like the blue line is right at the red line, and it's there for a while until DynamoDB finally scales up, and then finally our application gets a little bit more unthrottled. It never looks like this where the red line is, upwards away from the blue lines.
Right, like this is what I want every database scaling to look like. And that, unbelievable.
It seems like they just might be doing that by choosing their variables. Like the red line is what's possible and the blue line is what's happening. But what they really, if they really wanted to show it, would be like what the demand was. If they could figure out that the demand was above if that's what they were graphing instead of the actual, you might see a different pattern.
Yeah, so they're showing you consumed. They're not showing what's being throttled.
But I would expect the red and the blue to match for a certain amount of time.
Before it scales up. Right.
And then the red would exceed the blue. And then the blue would catch up again and sit there. And then the red would go above the blue, over and over again.
Yeah, it's a good point. It would be nice to see on here, like the blue line with whatever is in addition that is being throttled. Yeah. To know how long is your application being throttled before it scales up, because that's one of the exact reasons that we actually moved something from Dynamo back to, schema based, because we were having issues with Dynamo scaling at the levels that we needed it.
Yeah, because I just want to point out two peaks here, right? So we have this first bump. I don't know if you can see my cursor, but the first bump where it goes up, it just instantaneously touches, and then boom, it's up there, right? Red goes way up. And then if we go to the second peak, the red line is no longer waiting for the blue to touch it. It's almost scared of it, and it jumps up before it can get to it. And I have never seen that in an auto-scaling application. That is predictive scaling at that point. And if they can do it, that's amazing. This is also from 2 years ago, so who knows? But yeah, I would definitely like to see demand. That's a good point.
So this is a really good way to manage the cost of your database. Now, NoSQL databases in general can't do this, so these managed services are really valuable. A managed service like DynamoDB is really valuable because it provides the elasticity, which is a huge cost savings over time. In the middle of the night when your application is not doing anything, you don't really want to be paying for all of those server instances to be running, and so that's one of the nice things about Dynamo. All right, let's get into the NoSQL data modeling, and it's not for the faint of heart, right? But it wasn't really designed to be. It was designed to maximize the efficiency of your access patterns, and this is one of the things that as developers we're really going to have to understand and embrace because we're so used to developing with relational technology. And when you look at the data modeling in NoSQL, it's different, it's hard. Okay, there's a lot of differences between how I model data in NoSQL and how I model data in relational databases, but the bottom line is the data is relational. It doesn't stop being relational just because I'm using a different database. It's the same entity relationship model that we're going to build and that we're going to manage and that we're going to have to support with the application service. And it doesn't matter what type of application that we're building, it's all the same. It's social networking, document management, IT monitoring, process control. Every single application you can think of has some sort of data model that is relational in nature. So how do I deal with relational data in a NoSQL database? A lot of people call NoSQL, they call it non-relational. You'll notice I don't even use the word non-relational because the data is relational. It has to be or we wouldn't care about it. So when we get into how we've done that in the past, we've used this normalized model. And this is an example of a product catalog where I have products of 3 types. I have books, I have albums, I have videos, and you can see all the common relationships that we track and we manage with the relational database in this structure. We have one-to-one between products and books, albums, and videos. I have a one-to-many between albums and tracks. I have a many-to-many that goes through a lookup table to get videos and actors, because actors can be in many videos. So this is a complex set of queries that need to be executed, right, to get a list of all my products. 3 different queries joining up to 4 tables. And this is why relational databases cannot scale, because the CPU is going nuts, hopping all over the disk, pulling data off of all these tables, sticking it together in a denormalized view, and serving it up to the application layer. And on the
okay, SQL here is a declarative language, and you can do NoSQL-ish stuff using SQL. So just throw that out there. CockroachDB is actually super cool in this. It uses essentially Postgres, and it is a fully geographically distributed database. So, yeah.
The flip side, when I need to update that data, because what I'm really doing when I execute those queries is I'm populating application layer entities. When I need to update the application layer entity, well, what happens? The data lives in multiple places. So now I need ACID transactions, right? So a lot of the need for ACID transactions is really, the reason for that is because of the data model that we're using with relational databases. Sorry, I'm losing my voice, folks. It's been a long week already.
He was talking fast.
So maybe a better approach to this is to not do that. We don't want to burn that CPU like that. We want to take those hierarchical data structures, we want to collapse those things and build documents or collections of items within single partitions that represent these data hierarchies. And now, instead of having to execute 3 queries with various degrees of complexity, I'm executing one simple query that says select star from products. If I want to get all my books, select star from products where type equals book. Right? These are much simpler queries, much simpler access patterns, and you can see immediately why does the system scale better when I use this type of hierarchical data model, right, than this relational data model. Because I'm not executing as complex an operation to assemble the view. I'm just going and getting documents or collections of items out of single partitions. I don't have to go and join data and create these views. So when it comes down to it, there's really just a few concepts we need to understand when we get into data modeling in DynamoDB. The key concepts are really about selecting the partition key and the sort key. As we talked about, the partition key is about large numbers of distinct values. We want things to be uniformly requested over time, so maybe some bad examples would be status and gender. Good examples might be customer ID, device ID, things that allow me to kind of distribute that data. Selecting the sort key is about modeling those one-to-many and many-to-many relationships that we need to support in the data model and building a sort key that allows me to execute very efficient and selective patterns. This is what we're going to get into when we start talking about composite key modeling in a few minutes. But it's about querying across entities. With a single trip to the database, I want to get all of the items that I need to support that access pattern. I don't want to have to go back multiple times, go get my customer item, now go get all the order items for that customer. That's a relational pattern. And I see this all the time when I work with developers because they're used to modeling data relationally, so they do it that way, and then their access patterns become very inefficient because I'm really managing that join at the application layer as soon as I do that. Right? So what we want is maybe good examples of this. We talked about orders and order items, hierarchical relationships, which we'll get into in a few minutes. As we walk through the process, and it's important to understand the differences in the process between modeling an application in NoSQL and relational database. As a relational database, all I need to do is normalize the data, right? We have this neat thing, it's called third normal form. I could probably talk to almost anybody in this room right now who's listening to this presentation and say, here's my business problem, here's my entity relationship model, can you give me a data model for my relational database? And everybody be able to sit down and build that third normal form, right? And then we can argue about what queries are more efficient and add an index or two after the fact. But the reality is with NoSQL, it's the opposite. I need to understand every access pattern. I need to know exactly what the application is doing. Because if I don't, then I can't model the data in a way that's going to be efficient for that particular application service. So the first thing we want to do is understand that use case. What is the nature of your application? Is this an OLTP app? Is this an OLAP app? Is this a decision support system? There's a very different requirements for those applications. And
yeah, so it seems like this is like you can do a lot of this. Can't you do a lot of this like in Postgres with a materialized view? It's kind of like the same concept. Like, do you have to assemble the data ad hoc, or do you know in advance exactly what your view of it's going to be? And if you know what your view of it in advance is going to be, I mean, something like maybe kind of ignoring the materialized view, the benefits of a materialized view in an SQL database anyway.
Yeah, I mean, that's what I was going to say. Most people that are designing SQL databases versus Dynamo databases, most people that are designing the SQL database, they don't necessarily know what the hot use case is when it's being designed. They don't, you're adding indexes after the fact. So I thought he said something very important, which is you have to, what he's effectively saying is you have to know how it's going to be used up front, so that way you can generate the right way of being able to create a view. I don't know about you, but in my experience, most of the time the application data tier is being written before the view tier has even been thought about, at least in my experience.
Yeah, and doing it, having some flexibility of having a materialized view after the fact means that you don't have to like go back and redesign all of your tables if you want to change
your view, right? Exactly. Yeah. So I actually see that as a negative, even though I feel like this is saying that DynamoDB is completely coupled to whatever view and access pattern you have, which I don't consider that as a positive personally.
Yeah, I'm almost all right. Because it's almost like so wrong that it can't be how we're reading it, right? Like I want to give him a little bit of benefit of the doubt here. This guy's highly paid.
Yeah. I mean, he's selling to, and I mean, he might. Maybe we'll give him a chance. Maybe in 5 minutes, he'll explain what we just talked about.
I'm just saying though, if your view needs to change, you're not going to refactor all, terabytes of data to be into a new set of keys.
Right, and I'm wondering if there's like some kind of hybrid data model that he's almost assuming, or if he's almost assuming a microservice architecture where if you're really going to make that big of a difference in your data model, you're also going to be making a big change in your microservice. So maybe there is a data migration that you're going to do anyway because of that.
Well, yeah, but if you're willing to buy that, and you're willing to buy that it's a microservice architecture, and all of a sudden, oh, you want a new view? don't worry, go create a new microservice with another backend and, consume it from the current one, and,
Yeah.
and basically use CRUD operations to move the data.
Yeah, so I'm thinking like a big like data flow, and I don't want to just draw it here, but like the one microservice, to pull on his earlier example, might be responsible for returning orders for customers. That's its job. Now, when a new order comes in, we're almost going to do like a CQRS separation where the command is going one way, and then maybe it fans out into multiple microservices. And then like they each can be responsible for a different optimized view kind of thing, almost use cases. I don't know. I'm working backwards from what he's saying. So
if that's true, think about how many services you
yeah.
might for a database that, take a typical, SQL database. Think about how many microservices you might have to write. Because what you're effectively saying is that you need a different microservice for every type of join or store procedure that you ever write for a typical SQL database.
Yeah, no, I'm definitely trying to work backwards from our read of that, because that's definitely how I'm reading it too.
And there might be the horses for courses thing. There might be, just different sorts of applications that really are a lot more predictable up front.
The order use case, I think, is pretty friggin' predictable, like go get a list of historical orders for this customer ID. That is a very, very flat type of table structure,
Right. And, he did. Yeah, go ahead.
I was gonna say, and so like if you have a really predictable application that way and you need really massive scale, then this seems like, it would be a better fit for something like that, at least, than it would be for something that's, doesn't need the massive scale and maybe could benefit from more flexibility.
Yeah, and piggybacking on that, the whole system could still be using multiple data sources. So like that high scale, high use part that is mostly predictable could be using Dynamo, and then there's a relational aspect off to the side.
Yeah, I'm almost, the way that I'm almost hearing and reading into what he's saying is, well, if everything's relational, maybe at, startup stage where maybe you don't have a lot of scale, you start out with SQL, but then as you find hotspots in your SQL code, you migrate it to DynamoDB and microservice architecture that is predictable because you know what the hotspots are at that point.
Yeah, that's true. Yeah, because I'm thinking of a couple of applications that I'm working on now, and I could definitely put one of them in Dynamo because it's been around for 20 years, that application. We know what it's going to do. We know what data it's reading. Yeah.
Yeah, I can buy it if you understand how you're currently scaling. Trying to invent this though with like a greenfield product seems hard to stomach personally.
Well, I think you're supposed to build it for those common use cases, like they gave the example of customers and their orders, right? I know from talking with some AWS folks in the past, because I've asked about query flexibility as well, because Dynamo just did not seem to be well suited to that. And they said that in many of their architectures that they prescribe to their customers for query operations, they move more of that ad hoc querying to a tool like Elasticsearch. So Dynamo becomes sort of the system of record for the orders, sort of the one source of truth. And then if you want to look at those data, those orders sliced and diced many different ways, you would use Elasticsearch to do that. Not much different than an OLTP application, which is optimized for write operations, and then maybe on a periodic basis that data is shipped over to an OLAP, a completely different database system that's optimized for speed and querying, right? This is a typical problem with, even if you do a SQL system, the contention between OLTP users and users that are trying to query this data at the same time. And usually, even when we just had SQL databases, right, we would create replicas of that data and organize it in a way that would make it the most efficient for querying, including denormalizing that data in many cases.
Yeah. And to support that use case, I don't know if it was out in 2018. That sounds about when this came out, but I posted in the Zoom chat DynamoDB streams with Lambda triggers.
Right.
So that way, whenever you write data into Dynamo, you can actually trigger a Lambda to go do whatever you want. So whether that's syncing off to Elasticsearch or who knows what, you can do it. I think also DynamoDB streams can feed into Kinesis.
Yes, I think so. I mean, the issue with all of these, of course, is that other system, the say Elasticsearch, is not going to have that data in it instantly. Right. So if you go and update the table and come back, a couple hundred milliseconds later, it may not be an Elasticsearch yet, and you have to be able to deal with that. In many cases, that's acceptable, but it might not be in some scenarios.
And yeah, there's also, you can put in things like into Redis, right, for some kind of LRU cache.
Right. Yep.
Like, hey, I just wrote this thing. It's in Redis. It's also going to Dynamo eventually to show up in Elasticsearch.
Yeah. I mean, the issue, of course, with all of these is the fact that for a given moment in time, they're not all consistent, right? They're eventually consistent. And you have to determine whether you can tolerate that. And there's different technologies that are being used here. What if something breaks down in the communication between these different layers? I mean, this is all stuff that we didn't have to worry about when we had a single, relational database. But even when I had those, there was often contention between what does the OLTP system need and what does the reporting system need.
Right.
I mean, anytime that you have read replicas, you already had that problem of eventual consistency. Right. So.
Yep. I'd say that it's probably magnified even more when you cross technologies, right? When you're doing DynamoDB and Elasticsearch, it's going to take even longer.
Oh yeah. Well, it's going to take you longer, and there's more steps in the chain that can break.
Yeah.
Right. Exactly.
And so this serverless revolution, you have to wonder: are we actually making things more complicated?
Well, yeah. You also have to look at the cost too, because now I'm not just running DynamoDB; I'm also running Elasticsearch. So I mean, the original tenet of this presentation here was, it's cheaper. Well, maybe it's not cheaper if you have to put all this other, have to put all these other tools in to cover the holes.
Yeah, total cost of ownership is definitely why I get paid to do side work. Anyway.
And really, there's one of them that doesn't fit, right? That OLAP application just does not fit with a NoSQL backend. Define that entity relationship model. Know what it is. What is the data that I'm working with? What is the nature of that data, and how is it related? And then identify what the data lifecycle is, right? What's my archive backup? Do I need to TTL this data? What is the lifecycle of the data on the table? The next thing we're going to do is identify all of the access patterns of your application. So this is what I'll do when I sit down, I do my design reviews with customers. How do we read the data? How do you write the data? What's the write pattern? What's the read pattern? What are the aggregations that we're trying to support with this particular application service? And we want to document all of the workflows up front. Why? Because I'm actually designing a data model that's going to be very specifically tuned to those access patterns. And if I don't identify all those patterns, then I could be in a lot of trouble when I go out and try and deploy this thing. I might do a lot of work and have to unwind a lot of things I've done. So one of the things I hear a lot is use NoSQL because it's very flexible. I've done 1,000 NoSQL applications. I can tell you nothing could be further from the truth. NoSQL is not a flexible database. It's an efficient database, right? But the data model is very much not flexible. Because again,
I really appreciate that honesty. Just want to highlight that.
Because I'm building the app, and you'll see when we get into the actual modeling of this and how you actually build real services on NoSQL with complex access patterns, the more that I tune that data to the access pattern, the more tightly coupled to that service I am. So it's not really a flexible service, but it is a very efficient database to use at scale. So then the next thing we're going to do is we're going to actually model the data. And this is where we get into the common mistake everybody makes when they work with NoSQL applications. They start building multiple tables and they start building relational design models. It's about one application service requiring one table, right? And then we're going to get into that when we talk about the data modeling in a minute. We'll show you some pretty complex services that have been modeled down to a single.
I swear I didn't watch this beforehand.
I know. I think we've got. I think we came up with the answer, which is it's the microservice architecture. It's almost like a requirement.
Yeah, and one thing he did mention, like he is hammering home at scale now, right? So I think the high churn is going to happen at lower scale, right? Like you're not going to have an order system that you're changing the data model on every 5 minutes when you have 1 billion users, right? When you reach that scale threshold, it's well known.
Well, you're going back to the you don't know this up front. You don't know this on greenfield stuff.
Right. Yeah. No, I definitely agree. Like day one DynamoDB for a startup, let's say. Yeah. No, probably not great.
It's probably a stupid. It's assume that you're going to change your back end at least 100 times, and eventually, when you find out where your hotspot is, that's the thing to finally maybe consider moving into Dynamo.
Yeah, and there's one thing to kind of throw in there when you're at. It's almost like there's a middle point, right? At 0 scale, right? When you're trying to get your first few customers, you can use literally any data storage you want because it doesn't matter. Everything's going to be fast at n equals 1. When you get to mid-tier scale, now you're going to be hurting. But then if you do hit large scale, well, you'll be happy with it. So there's that middle ground I think fails.
And if you're hitting large scale, you sure as hell know what your hotspots are by the time you hit them.
Right, yeah, yep.
And you probably have more money to spend to, hire people to fix stuff.
Right.
True.
Available for hire. Anyway.
Table and identifying those keys and how we're going to access the data and what are the actual queries that we're going to execute. Define your indexes for your secondary access patterns, and then it's just an iterative process, right? Just like any development process, we're going to review, we're going to repeat, we're going to review, and we're going to get this thing down to a science sooner or later. All right, so complex queries, right? It's all about the questions. Computers give you answers, but we have to ask the right questions. So they're not always useless, but some people have thought so. One of the things that NoSQL databases aren't so good at is actually answering those complex questions, right? I mean, I need to know what is the count, the average, the sum, the maximum, the minimum in a given set, all kinds of complex computed aggregations, things that may be stored procedures. One of the things about DynamoDB is really neat is this thing called DynamoDB Streams and Lambda. It's like the best stored procedure engine in the business because it's completely disconnected from the table space. One of the things that we did with Amazon's retail organization, and one of the reasons that we migrated off of Oracle was because we had a problem with service teams deploying stored procedures into an Oracle server that was shared across multiple teams, and maybe somebody would deploy some bad code and all of a sudden we'd have 3 or 4 services or more going belly up because the processing space of the head node of the database server got knocked sideways. One of the nice things about Streams and Lambda is all of the processing of the data occurs in a different processing space than the table, so you don't have to worry about impacting the availability of your DynamoDB table. So we can deploy really bad code to Lambda, and it's not going to really kill us. We don't want to do that, obviously. So the way Lambda works is, it works in conjunction with the DynamoDB stream. Stream is the change log for the DynamoDB table. It takes all write operations, will appear on the stream. Once the data is on the stream, it can invoke a Lambda function. That Lambda function has 2 IAM roles. We talked about, the security fine-grained access control. Lambda has an invocation role which defines what it can see or what it can read off of the stream. Which items can it see? Which attributes in those items can the Lambda process actually read? And then it has an execution role which defines what it can do. What other services within your AWS account space does it have access to, and what permissions does it have on those services to work with this data? So what do people do with this? In this example, not very much. It's just dumping those attributes out to the console, but it's code, and code can do anything. People do lots of things with it. One of the most common things we do with Streams and Lambda is computed aggregations. Right, people need to understand what are the averages, the counts, the sums. One of the nice things about MongoDB when you're working with small data is aggregation framework. How many people have used aggregation framework for MongoDB?
So in our previous discussion, I think we covered the next 5 minutes. That's cool. Because here's our cloud search that Pete was talking about. Kinesis, Firehose, Lambdas, how to make materialized views. This is cool. What else do we want to predict? Anything else?
Eventually, I'm willing to bet he's going to say something like, okay, by the time that you take your SQL and turn it into NoSQL, look at all these pieces that you have to actually deliver that work together.
CloudFormation. Anyway.
A few, okay. I loved aggregation framework when I was in MongoDB until I had to scale it. And I realized it doesn't scale too well. One of the nice things about this particular design pattern is as we read data off of the stream, we can compute these running aggregations, these counts, sums, averages, or complex computed metrics that we need to maintain at the application layer, and then write that data back into the table as a metadata item. So for things like time series data, maybe I have time-based partitions. As I load those time-based partitions, I can execute my aggregation functions and produce all those time series metrics and write that metadata item right back into that partition. And a really neat thing about time series data is once it's loaded, it don't change. Right? So we don't have to worry about that metric having to be calculated 1,000 times a second. The data gets loaded, the metric is calculated, and now it can be read 1,000,000 times. And I don't have to recalculate it every time. This is what we want to do with NoSQL. We want to offload the CPU. We don't want to have to compute things. We want things to be pre-computed. So this is a really neat design pattern for that. We have lots and lots of customers that use that. Plenty of other things we can do with Lambda, update cloud search or Elasticsearch or other indexing systems. Push the data into Kinesis Firehose for stream processing, interact with external systems. Again, Lambda is just code, and it can do anything. The other thing you can do is it doesn't have to always be Lambda that reads the stream. If you have a high-velocity workflow, then maybe Lambda is not the most cost-efficient thing to use. Maybe I'll stand up an EC2 instance and create a static stream reader service. That's perfectly acceptable as well. We have lots of customers doing that. So realize that streams and Lambda is there for you to execute those stored procedure type operations or complex computed aggregations. Certainly a valuable service for doing that. All right, let's get into what we deal with composite keys. And I love this quote because it's perfect, right? Most people use NoSQL as a key value store. That's not the way that NoSQL is the most efficient way to be used, right? We want to actually store our hierarchical data in the table, so to speak. So how do we do that? In this case, let's talk a little bit about composite keys. And in the use case here, we have maybe players for a particular game. They have sessions. Sessions have state. What I'm interested in is all of the given sessions for a given user that have a state of pending. So game invites, whatnot. In this particular case, I might have a table that is partitioned on the opponent, that is sorted by the date. And if I want to get all of the sessions for user Bob sorted by date and filtered on pending, DynamoDB can support this because we give you two key conditions that you can actually evaluate. Two range queries. The first one applies to the sort key. That's the sort condition. That's the date condition. So in this case, I'm saying there is really no sort filter. I'm just saying give me everything ordered by date. Since the sort key is the date, all the items are going to be returned sorted by date. That's great. But I'm really only interested in pending items, so I'm going to say filter on pending. That's the filter condition. So the sort condition applies before the read. So it'll give me a nice selective read. The filter condition applies after the read. So it'll knock out the items that I'm sending back across the wire, but I'm still paying to read those items. So the cost of that read is the same as whatever the sort key dictates. This is okay in this particular example because I really only have 3 items and only one of them is being filtered out. All 3 of those items really are less than 1 RCU, so the cost of that query is equivalent, right? Whether it was more selective or not. But let's say there was 10,000 items in this particular user's partition and only 2 of them were pending. Maybe I don't want to read 9,998 items just to return 2. So one of the ways that I could do that, and the only way to do that, is to create a composite key. Composite keys are how we create hierarchies using the sort key structure. So if you think of what we're going to do here is we're going to take the status and the date, we're going to concatenate those things together. We're going to create one key called status date. When we push back to the table now, you can see what that view looks like. It's like a faceted search. I can say, give me everything for this particular user that starts with pending. It's going to give me only the items that are pending, and it's going to be a nice selective read. I can say starts with pending underbar timestamp 1, or between pending underbar timestamp 1 and pending underbar timestamp 2, and I get a range of items within a given state. And again, I get a query across states. So think of this like a faceted search type. And what I'm really doing is creating a hierarchy. And we'll show you how to do that when we get into the advanced data modeling here. And advanced data modeling is about thinking about the data, right? Nothing does itself. The way the OLTP apps use data, again, is about hierarchical structures. They use entity-driven workflows. The data gets spread out across tables and requires complex queries to be able to populate these application layer entities. It requires multiple queries to be able to update the entities. And it's a primary driver for ACID when we get into NoSQL databases. However, so when we denormalize the data and we create hierarchical data items, then maybe I don't need much more than atomic updates. There's still times when we might need ACID transactions. One of the good ones is in maintaining the version history or creating new items that actually get created in multiple passes and committed all at once. So in this particular example, let's talk about, we have items on a table. These items have maybe a first item that we put into the table is the V0 item. It's a copy of the V1 item, and that contains the current data for this particular partition. So when a customer wants to come in and get the most current version of that particular item, he says select star from table where the item ID equals 1, and the sort key starts with V0. He's always going to get a copy of the current version. So if we look at the state of this given partition, it looks like somebody came along, they created item 1. Initially it was version 1 and there was a copy of version 1 in V0. Somebody came along, they created version 2, they committed version 2, they updated the version 0 item, they just clobbered it with a copy of V2, and they updated the current version attribute to indicate that it's now version 2. So when the reader comes along, says select star where starts with V0.
There's a question in chat. I don't quite understand.
It was during when he was talking about composite keys, which was basically his answer was, oh, can concatenate two completely different attributes together. So the in progress and pending, when he was talking about the in progress, pending, and the date, he basically concatenated the two together into the sort key. It was before this section right here. So later on in this same section.
Here we go, right here.
Yeah, like this seems like a complete and utter hack.
Yes. But it's also, I would say, extremely functional, right? It achieves the goal fairly well.
Yeah, I've seen compound keys like this for decades. I mean, it may not be nice that they're not in separate fields, but this is a very common pattern.
Yeah, and so long as you can express the data in a sorted order that gets sorted in the right way in a string, which seems like, I don't know if that's always possible, but it seems like it should usually be possible.
Yeah, that's typically why it's done that way.
Yeah,
and it's highly efficient.
Please don't have multiple words that are similar, right? That stem the same, right? Like done and donning may not be a good combination. I don't know when that would happen, but might not work as well that way. Although maybe it's just fine. So, but yeah, they're just combining things. I think we were here.
Partition and looks and says, give me the item that starts with V0 is actually going to get V3. So neat things about this particular pattern, I have an audit trail, right? Everything that changed, what version it changed across. You can decorate those items with the who changed it. So all kinds of nice things you can do. I get the same type of visibility I'm used to with ACID transactions, read committed, read uncommitted. I can read committed, starts with V0, read uncommitted. Scan forward index false, limit 1, gives me the item that might be being worked on, so on and so forth. So it's a neat way to be able to maintain version history and have some sort of transactional workflow against a single item. Now we get into multiple items, we're going to talk about started getting into some real data modeling here. So in this example, I'm going to use a pretty simple, this is an internal service that we have at Amazon. It's a resolver service for configuration items. Configuration item, we create the resolver groups. We associate the configuration items to those resolver groups. And then we have contacts for those resolver groups. When new configuration items come in, we email all the contacts that are associated to a given resolver group. And so the data model looks something like this. We have a resolver group entity. There's a many-to-many relationship between contacts and resolver groups and between configuration items and resolver groups. And there's a couple of transactional workflows that we have to execute, right? We want to add configuration items to the resolver groups all at once or not at all. And a configuration item can belong to multiple resolver groups. So, and multiple configuration items might come in together, and we want these things to be committed to the resolver groups all at once or not at all. And maybe contacts might need to be added to resolver groups as well, transactionally. We might want to update the configuration item data transactionally. There's a lot of workflows around here that require some transactional interactions with the data. And DynamoDB, if you're up to speed this morning or this early afternoon, we announced a really cool new feature, which is Transactions API. We have now a transact write items, transact read items API, where we can actually support synchronous updates, puts, deletes, across multiple items, full ACID compliance with automated rollbacks, up to 10 items within a transaction, and supports multiple tables, although you should not have multiple tables. I didn't want them to do that, but they did that. It's okay. There are use cases for multiple tables. It's not, I try to drive things to a single table, but even myself, I'll get into the point where, no, let's split the data up. But generally speaking, it's a single table. So good use cases for this, commit changes across items. Absolutely, love it. Conditional batch inserts and updates. Right? We can have multiple conditions defined within a transaction. If any of those conditions fail, none of those items will get written. That's a great use case. Really bad use case, maintaining normalized data models. Please don't do that. So transactions is here for you, but it's not a crutch to make your relational models work, all right? That's actually going to be a real bad pattern for you. So how does this work in DynamoDB with the single table? In this particular case, we have resolver group partitions and contact partitions. What we've done is created a pretty simple adjacency list. An adjacency list is a simple graph. As we denormalize the contacts across the resolver groups, what I'm really going to do is create a copy of that contact and reinsert it into the table with a different sort key. And that sort key is the actual resolver group ID. So now what I've done in my contact partitions is I have a copy of the contact for each resolver group it belongs to. If I need to add resolver metadata into the resolver group partitions, and then I'm going to add configuration items into those resolver group partitions as well. Now when I get into the transactional updates here, what's going to end up happening is maybe I have a configuration item I need to add to multiple resolver groups. Transact write API gives me the ability to execute that insert to both of those partitions and guarantee that both of those inserts will commit or not commit, right? It's up to, when the transaction, API to manage that process, not the application layer anymore. Maybe I need to update the transaction status. Maybe I want to cancel an item and I can add multiple conditional checks. I can say, cancel this configuration item across all resolver groups as long as none of them are in progress. That's a really valid use case for us, right? Because sometimes configuration items get pushed into the system and somebody goes, oops, we don't want to do that. So pull it back, right? I need to call that configuration item back. Maybe I need to update the contacts email, right, across multiple resolver groups, and I don't really want to do that outside of a transactional envelope. Again, so multiple ways that we can execute transactional writes in this particular use case, and this is a really good example of a single table design pattern that maintains a complex entity relationship model, right? We have configuration items, we've got contacts, we've got resolver groups, they all live on the same table. The metadata for all of that lives on the same table. And just to kind of show you how that, as we add one GSI to do our reverse lookup, right, I can look up contacts by resolver group on the GSI. Remember we denormalized our contacts across the resolver groups, so if I want to go back to the reverse lookup GSI, I can read the partition key for with the resolver group ID and get all of the contacts for a given resolver group.
Yeah, so that's cool, right? I can essentially have two tables that I would have had in Postgres in the same table in Dynamo.
Right. Now, there's one thing that's interesting with this. Look at the uniqueness of those partition keys. They're not very unique, right? So typically, a little while ago, we were told that partition keys should be very unique. You shouldn't have them clustered around relatively few values.
Yeah, I mean, You're right. Wouldn't this hit a scale issue?
So that was the reverse lookup. So maybe that's different.
Well, no, because the partition in effect in this case is like a table name, right? So
sure.
So if you're going to have a lot of access now,
well, it's a composite key, right?
It's a
It's
composite key, but things are broken out by the partition key.
right, the partition key, like contact 1, contact 2. So that's almost like
Okay.
table name and then ID.
Yeah, all right, you're right. You're right. It's not, yeah, it's they don't all say contact. They say contact 1, contact 2, etc.
Right.
So
Yeah. So this is
yeah. So I
building
guess it
onto
is.
that
Right.
string concatenation.
Yeah, it is. It's more concatenation. Yeah.
Now the string sorting, I wouldn't use a UUID for sorting. I mean that there is no sort on that.
Well, it's not, yeah, they're not using it for sorting. They're using it for querying. So they can go in and say, give me resolver 1, and then I have this key.
Mm-hmm.
And they're using the sort just to quickly find that entry.
Okay, sure. Yeah. That makes sense.
Yeah, that's the misnomer, is that they call it a sort key, but in a lot of cases you're not actually sorting on it. It's just a fast way to get to the data.
It's just we know where it is key. Well, not the sort key. The partition key is hashed, right?
Right.
Is the sort key hashed too? I don't think.
No, I don't think so.
Yeah. Right.
Okay.
The sort key really couldn't if we're going to sort.
Right. But in this case, yeah, in the case of resolvers, they're not likely to sort by UUIDs.
Yeah. So one thing that we haven't done yet is have a JSON object or something as one of the attributes, and that's where you put all of the resolver details. He's just straight up making a partition key called resolver and saying, no, same table. Go query it over here. Here's your join.
Right.
That's cool. All right.
Has anyone done this in the real world on the call?
I've seen this done. I'm trying to think if I've ever actually done it, but I've certainly seen this before. This concept of, in effect, storing multiple tables inside one table.
Interesting.
Yeah, this is not an uncommon thing that's done. You almost have to watch this stuff multiple times, because my brain doesn't work this way. It's still stuck in the old relational world, because it's so many years, you've been used to thinking that way, and this is just a totally different way to think. It's kind of like when I first started using the relational databases, I didn't think that way either, because I used hierarchical databases prior to relational ones, and SQL was a different way of thinking, to pull back things in terms of sets of data. So, in some ways, this is a throwback to some of the ways things were handled prior to relational databases. Like when I worked on the mainframe and we did IMS and stuff like that, which was, a hierarchical database, or didn't really use a database, but used a whole bunch of indexed sequential files like VSAM files and ISAM files and stuff like that on the mainframe, used techniques that, surprisingly are similar to this, even though some of them were invented 50 years ago.
I mean, I don't know if it is really all that surprising if you think about it, because isn't that what the cloud is and managed services is? It's kind of going back towards the mainframe way of doing things.
Yeah, there's a lot. When I first did web development and I saw, the whole notion of stateless programming and stuff like that, I hearkened back to an IBM CICS manual that I read that was copyrighted back in 1971, and it talked about pseudo-conversational programming, which was basically stateless programming. IBM had to use fancy words for everything, but a lot of these concepts were invented in the late 60s and into the early 70s to provide high scale. And you had, at that time, machines that maybe had, 16K or 64K of memory, but you still had hundreds of users that were online at any given time. And the only way these systems could provide that level of scale is to do it in a stateless way. And they had, the equivalent of session variables. They were called temporary storage queues in CICS, but, it worked surprisingly in a similar way.
Yeah.
I mean, that kind of goes back to what he was saying earlier about learning from the past, right?
Yeah. I mean, thank God the tooling here is light years beyond what we had on the mainframe, right? It was just pathetically bad, the tooling. But some of the concepts that enabled, and I remember at the time being surprised at how well this stuff worked and how well it was thought out and how we were able to support thousands of concurrent users on, what was relatively, by today's standards, very modest hardware.
I mean, I know some apps that can't handle thousands of concurrent users.
Yeah. Oh, there's, unfortunately, there's a lot of those. Yeah. But, yeah, I remember, doing all kinds of stuff with deadlocking and, how these OLTP systems could actually determine when there was a conflict with two users who had done the most amount of work and appropriately cancel the transaction that had done the least amount of work, stuff like that. And this was stuff that existed 35 to 40 years ago.
That's cool.
It's almost like we've all gotten lazy as the hardware has, it's always been to vertically scale recently. But back then there just wasn't that much hardware, so you had to come up with more intelligent ways to deal with it.
Right.
I would like to find a talk on mechanical sympathy.
Yeah.
Yeah, we didn't have flexibility though. So the ability to query that data, tough. You either knew the primary key or you're sunk. You weren't going to be able to pull that data back. I mean, I remember working on a system where if you didn't know the item ID for the bill of material thing that you wanted to update, good luck, because there was no good way to query it other than based on the primary key. Stuff like that they were not terribly flexible systems. And then that data later on was copied over to DB2, which was one of the first SQL systems that I worked on. And now we had query flexibility, but it was two totally separate systems. One for OLTP, which was on IMS. Then that data was copied over to DB2. In that case, on a weekly basis, before it would show up in DB2. Now this is 35 years ago. So
yeah.
Oh man. That's awesome. All right. We got what, 15 more minutes in the talk?
Yeah.
Let's see if it takes us an hour.
Let's hope not. But then we're getting to the meat now.
Yeah, right. I mean, I hope we don't have to pause it every 5 minutes, but I feel like we're going to have a lot of cool things coming up. So.
Yeah.
Read the partition key for with the resolver group ID and get all of the contacts for a given resolver group. Or I can get all of the resolver groups for a given configuration item. Right, again, so all I've done is I've taken that primary table, and I've created a reverse lookup on the partition and sort key. So now the sort key is the partition key, and the partition key is the sort key for the GSI. It gives you that kind of reverse lookup. So this is a way to be able to maintain many-to-many relationships. Right? I mean, if you go back to the ERD here, we had, we've got a many-to-many between resolver groups and contacts, many-to-many between configuration items and resolver groups, and in this particular data model now, I've maintained that many-to-many relationship across all of those entities using the primary table and the reverse lookup GSI. All right, getting into hierarchical data. That was a little bit of some data hierarchies we work with there, but this is another service we use internally at Amazon. This is for getting office information. If we go into our wiki page and we click on a particular office building, whatnot, this is the service that it's going back to, or you search for offices. In this particular example, we have pretty straightforward linear hierarchy: country, state, city, office. On the table, we're partitioned on the country ID. We're sorted on a composite key, which is the state, city, office ID. So now the access patterns here might be, say, give me everything in USA. In the United States. Query the table where the partition key equals USA. I'll get every office in the United States. I want every office in New York. Okay, country ID equals US. City starts, or sort key starts with NY. Gives me everything in New York State. Everything in New York City starts with NY, hash NYC. Gives me everything in New York City. So a really nice way to be able to take a linear hierarchy like this and just slice it up into a composite sort key and be able to support multiple access patterns, multiple groups, multiple aggregations. I don't need multiple tables. Again, if I tried to do this with multiple tables, just think of the access that I'd have to execute at the application layer. Oh, okay, let me get the country ID. Let me go back to the state and get me the states, in that country. Oh, right, okay, this state is New York. Let me go back and get all the cities in New York. Now let me go back and get all the offices in those cities. That's a lot of round trips. That's a high latency and a very expensive operation that you're going to be executing if you implement this in a relational pattern in NoSQL. Why? Because there's no joins in NoSQL, because joins are expensive, and that's why relational databases don't scale. So when you hear people say that NoSQL is missing joins, well, you say you're missing the point, right?
Ooh, burn.
All right, so complex relational data. We got a little bit of a picture of that when we're looking at that configuration management service. This is more of a, let's go into a theoretical delivery service, right? So I created a fictional delivery service. It's called Get Me That. Get Me That gets people things, right? People are busy, they need stuff, right? Download Get Me That. Browse stuff, get stuff, tell us where to put your stuff. That's what this does. So it's a very simple service, but it's not a very simple entity relationship model. When we look at this, we have customers, vendors, orders, items, drivers, right? Customers place orders, vendors accept items from those orders, drivers deliver those items, drivers have status, current status, they have 5-minute status, they have 10-minute status, because we want to kind of schedule things efficiently, right? So let's see what that actually looks like, when we get into the access patterns. We're talking about 10 or 12 different access patterns for this application, right? I want to get customers by date, vendors by date, or orders by customer by date, and vendor by vendor by date. Order details, order items, status, delivery, deliveries by drivers, driver status for scheduling. So it's a very complex set of access patterns, about 10 or 11 access patterns we need to support in this given application. Pretty straightforward thing to do with a relational database, right? Just going to create this, normalized view of the data, execute a bunch of queries across here. But again, as we talked about, the joins are going to be very expensive, especially as we scale the data set, right? And I've really noticed a trend, and I used to say that NoSQL is for OLTP at scale, and if you're not dealing with big data, then maybe you should be looking at other technologies. And what I'm really finding these days more and more is that the common app is becoming a big data app. So it's not so much, I really do believe these days that NoSQL is the future for the vast majority of workloads, just simply because of the scale of the data, and these relational models break when I try to execute those complex queries. So the NoSQL approach here, this is a little bit of an eye chart, but we're going to walk through it. This is all of that entity, all those entities stored on the same table. The first query I might get is say, get me the customer's information, and I would query the table by customer email. That's going to use this.
I can barely read this. Right, so
is the partition key, and my sort key value would be customer. Give me the customer item for this customer, for this email. That gives me nice selective query out of that customer's partition. Give me the customer's orders in the last hour, in the last day, in the last week. I'm just going to timestamp all those orders. I'm going to insert those orders into the customer's partition by email. Now when I query the customer's partition by email, I should give it a date range as the sort key condition. I'm going to get a different set of items. I'm not going to get the customer's metadata. I'm going to get the orders that the customer gave over that time period that I've specified. So again, I'm slicing the data into these partitions, out of these partitions to support the specific access patterns of the application. I want to get the vendor data. Anyone from Austin? Austin, there you go. You should recognize these vendors. Some of my favorite restaurants. If you're ever in Austin, go to Torchy's Tacos. Love it. The best barbecue in Austin is Salt Lick. Anyway, so I want to get the vendor's data. I just select by the vendor ID. And I want to get the driver data. I'm going to select by the driver's email. I want the driver item. In this particular example, the drivers are drivers and the customers are customers, but nothing prevents me from using the same email for a driver and a customer. I would have different metadata or different items in those partitions. They would still support the same selective access patterns. As we even go further, I want the driver's status by 5-minute, 10-minute current status, 5-minute, 10-minute status. I can get that by driver. Just saying select by driver starts with GPS. And then we go into the indexing. So the indexing is about overloading the keys. So if you look at the key attributes on these items, the order items are going to be sorted on the indexes by email, by order ID and email, by vendor ID and date across GSI 1 and GSI 2. Then as we get into the drivers, GSI 1 is totally different. It's not using the same key values, but it's overloaded using the same name for the attribute. So we'll see when we get to the index, these items are actually going to show up, but I'm indexing the driver's GPS coordinates by sector. Because when a vendor's order comes in, he's in a particular sector, I'm going to want to know what driver is going to be available currently, 5 minutes from now, 10 minutes from now, whenever that order should be done. So I can do my scheduling, and then I'm going to index the order items across those GSIs as well by timestamp and by customer, and by timestamp and by vendors. So when we look at the GSIs now, it's kind of neat. When I can query the GSI 1, and I say query by order ID. It's going to give me all the items for the given order. It's going to give me the customer that ordered it. That's a nice query. I don't have to go back and, several times to the database to get if I have an order, I can get all of the metadata that's interesting, all the details for that order just by querying the GSI by order ID, single round trip. This is what we want to do with NoSQL data modeling. We want single queries to deliver multiple entities. In this case, the orders the items for the order and the customer's information delivered in one query. I can query by sector, and I can get drivers that are in a given sector and what their current status is in 5-minute or 10-minute intervals using the appropriate sort key conditions, right? Current status, 5-minute status, 10-minute status, by sector, right? So a nice way to be able to solve the traveling salesman problem, if anyone's familiar with that one. That's a tough one. This actually is a good way to do that. This comes out of a customer design review that I had with them. That was a problem they were trying to solve. If I go back to GSI2 now, I can query GSI2 by vendor ID. I can query GSI2 by driver ID and get the orders by vendor by date or orders by driver by date. What's the driver delivering? What did he deliver in the last hour? What's my vendor delivering? What's he delivered in the last hour? Right? So these are the access patterns of the application that give me the ability to support all of those complex access patterns. I've got the entire entity relationship model stored in a single table. I have only 2 GSIs. So the other thing I hear a lot with DynamoDB is, you only have 5 GSIs. We can't use DynamoDB because we only have 5 GSIs. I just showed you how to support 12 access patterns with just 2 GSIs at a table. Now let's get into a real world example, which is even a lot more complex. And when we talk about this service, this is the Audible ebook sync service. This is how many people have Kindle. Okay, quite a few. If you have Kindle, you have, and every ebook you buy, you have access, if you have a Prime membership, you have access to the Audible ebook version. And the Audible ebook is obviously just, when you play on your Kindle device, you play on other devices, there's a lot of different relationships in this service that need to be supported. So a given ebook can have multiple audio products associated to it because it depends on the device it's being played on, the format of the audio files that need to be played. An audio product can have many audio files. So there's a many-to-many mapping between ebooks, audio products, and then the ACR info table is the sync file information. So if I pull into the driveway listening to it on my Alexa in my car and I walk in, I start listening to it on my laptop or my Kindle, I'm going to want it to start at the same place so that ACR info file has a many-to-many relationship between itself and the audio products. And so these guys were out there trying to figure out, they had a lot of downstream and upstream consumers, they had 20 access patterns, they're trying to figure out how to deal with all of this with 5 GSIs, right? Select by ebook SKU, select by ASIN, select, all kinds of different access patterns they need to support, ACR info, ACRs, and so they were having a terrible time trying to map the data into a single table implementation, and they're and you're thinking about going down the relational approach. When we came in, we gave them a pretty simple table structure. As they insert the audiobooks into the table, one of the things they were interested in was the audit trail. When the A-book ACR file changed, they wanted to know who changed it and why, so we gave them that V0 design pattern so they can implement, the current item is always V0 on the A-book ACR. We have 2 partitions on the table. We have an A-book partition, we have an E-book partition, and then there's an item that we insert into the A-book ACR partition that associates the A-book ACR to the E-book. So once we have all of this data laid out, then what we've done is created the GSIs. There's 3 GSIs on this table. If you notice that the GSI1, GSI2, and GSI3 don't always contain the same data type, and this is because, again, they have so many different access patterns. And what ends up happening is on the table, on the GSIs, it looks like nonsense. It's just a bunch of items sorted by all kinds of arbitrary dimensions. I mean, one particular GSI is totally, who knows why. I mean, I might query by A-book ASIN, A-book SKU across multiple GSIs by pulling different items out. What ends up happening here is that the computer is what's reading it. The sort key is what defines what comes back off of the GSI. And what we ended up doing was just taking their 20 access patterns and extending the table, so to speak. Again, big eye chart here, but it's not terribly difficult. If you look at the first 3 columns, that's what they gave us. Then what we said is, okay, query this table or this index with this sort key condition and these filter conditions, and that will satisfy your access pattern. So these guys basically, we did 3 indexes, 1 table, 20 different access patterns. I have satisfied I've done single table designs for applications that need to satisfy up to 30 or 40 different access patterns. okay, with extremely complex ERDs. As a matter of fact, we have a really good chunk of information up there on the website for you. It's the best practices for Amazon's DynamoDB. It was just updated about 6 months ago, brand new content, and it has a really complex schema in there. I think it's 27 tables, 30 different access patterns. It shows you how to map the whole thing into a single table. So I would definitely recommend that people take a look at that. It talks about an extended design patterns, a lot more than what I've talked about today. And
where did he say that was? Because I'm going to need to go through that again.
I don't think he gave a link. He just said it was available.
Right.
You know, there are a bunch of books out there that Amazon's put together for this. Because this thing is 2 years old now, so who knows? There might even be a newer one.
Yeah, that's true. Huh. I wonder if there's another video.
Is there a link maybe in the description for this YouTube video?
When it finishes, I'll check.
Okay.
Unless somebody else wants to look. Because if I do that, then it's just going to mess this up.
And I'm totally running out of time, but I have one more thing to talk about. It's just going to take a minute. It's a serverless paradigm, and if it's one of the things about, I like this quote because it's Linus Torvalds told us, right? It was cheap home computing that changed his life. Well, think about cheap data center infrastructure, because that's what serverless is. This is a really good example of an application we built for Amazon's CDO, Amazon's SA organization. They wanted to be able to get customer feedback, anytime feedback. So if you get an email from an Amazon SA, it's going to have a link in the signature. It says, rate my interaction. When you click that link, you're actually interacting with this application. It has pull down an HTML form from a secure S3 bucket. When you hit the post button on that form, it interacts with the API gateway. API gateway calls a Lambda function to process that data. When we wrote the application, it was we didn't have encryption at rest, so we actually had to push the personally identifiable information up into an encrypted S3 bucket. Now we can, I'm sure they've actually changed the application to store it all on the Dynamo table. And that unencrypted searchable metadata was stored on DynamoDB originally, and then we would email the manager and let him know that feedback had come in. Really neat application. We built very quickly. It just took us about a day or two to actually design and deploy. It deploys for pennies a month is the support cost on this. Right? And the nice thing about this application is if it could scale to a million users if it had to, all I need to do is turn auto scaling on that DynamoDB table, and it goes. So that's a really neat aspect of serverless, is that you can really get things out there, you can deploy it, it's cheap, that code just sits there until people actually need it. You can prove the application before you pay for it. It's not just fail fast, it's fail cheap now. Right, this is the cheapest data center infrastructure you're ever going to get your hands on for launching new application services. So I definitely recommend that you explore that serverless framework. So conclusions, NoSQL is not non-relational. Don't use that word. It's a bad description. Okay, the ERD still matters. Relational database is not deprecated, but we want to use NoSQL for OLTP database, for OLTP or DSS at scale. That's the sweet spot. And then use that RDBMS for your OLAP or OLTP when scale is not so important. Generally speaking, the common case is the big data case today. So thank you very much. That's what I have for you today.
Whew. I feel like I learned some things.
There you go.
Absolutely no links in the description.
No, we'll have to do some searching around.
This nice person gave us
that was really nice.
An index.
That is nice. Because the first part of this was, I don't know, a bit marketing-y. It wasn't really the meat of it.
Agreed.
Yeah, I like the TLDR in the chat. Tables and tables. I mean, that's basically a really good, representation of where he ended.
Kind of.
Yeah. Yeah, there's definitely. I definitely did not think of that. Right. But it makes sense. Like, there's no reason you can't do it.
Right. Yeah, you just have to, I guess that's the whole thing. You got to get comfortable with these sort of compound keys, right? Because we just had that discussion about these, because that's what it is. In a lot of cases, those partition keys are, in effect, a compound key. And
you also have to be very comfortable with the fact that every entry in the table is not equivalent, right? Because that's the big
Right.
thing. That's the big thing going from SQL to NoSQL.
Yes. Yeah.
Yeah, it's not even just like in Mongo, right? They kind of push you to this idea of collections, right? So it's like a collection of orders, a collection of drivers, a collection
Right.
of items, whatever. No, F that. It's a collection of all the stuff,
It's a collection of rows from his perspective.
right? It's just like,
The-
yeah, we're just scattering them across all of the nodes. Okay, that's a partition key. How do you want me to scatter them? Got it. Thanks. And then, okay, now that they're there, how do you want to kind of sort them and find them?
Well, yeah, it's that sort key that does that, lets you do that filtering. But then, even then, just because you got a customer record, if you will, doesn't
Mhm.
mean that all customer records are the same, right? You could introduce new attributes over time, right? So that's
Right.
the other one that people are not used to. The fact that, I mean, I think in most cases these things don't change a lot, but you got records you inserted 3 years ago, they may not have the same content in them that a new record does.
That's
Yeah, I
true.
mean that's where your app tier would have to deal with that. You know that API versioning, for lack of a better term.
Right. Yep.
Yeah, I think there's one thing though that I know that I need to learn next, and that's GSIs. It seems
Yeah.
like if
Yep.
you don't know how to use GSIs with MongoDB, you almost shouldn't even bother.
You mean with DynamoDB? You said
Yeah,
MongoDB.
If you don't know Dynamo or GSIs in DynamoDB,
Dynamo, yeah.
don't use DynamoDB.
Except for well, as long you can still use DynamoDB, but yeah, you're not going to be able to pull the data out different ways, right?
Yeah,
And
you're not gonna have as good of a time.
right. It's or
It's
well, it's
it's getting the different views, right? I mean,
those
it's
different
because-
access patterns. I mean, that's
Yeah.
what he was just talking about, the different access patterns. Now, he described how he was writing into those GSI attributes on the different records, right? Different values. Now, I could imagine over time, if somebody said, like he gave the example with the, I don't know, was it 20 odd access patterns that they had, right? That somebody then said, well, that worked great for 2 years and now the business changed. Now we need more access patterns, right? Well, you're going to have to go back through that data and fill in the GSI information for the new access patterns, potentially.
Yep.
Right? Which could be quite slow if the table is really, really, really large. I mean, not to say that if you were using a SQL database and you needed, to add new attributes or indexes, that would necessarily be terribly fast either.
Right. I mean, I think if you've worked with sufficiently large data sets, you've had that index being created for a couple days.
Right. Yep.
Yeah.
And it happens.
Right.
I think that's actually it would be interesting to see a case study of someone that migrated to Dynamo, and then as their access patterns changed, how well did the total cost of ownership of Dynamo actually work for them? Meaning, like adding in new GSI indexes or trying to add values after the fact. Because a lot of people depend on being able to do queries on the current data and the SQL side to be able to determine, all right, are we in the right place, or are we, how do we migrate to the new place? I'd be curious to see, a migration once you're already in Dynamo and have to add new indexes or sort keys or what have you.
There you go. All the answers in 10 minutes. It's
Yep,
kind of
this
like
is-
those old books that used to be, what is it, teach yourself topic X in 24 hours.
Yeah, in a month of lunches.
Yeah, exactly. Now you can do it in 10 minutes.
Yeah, one lunch.
It's GSI at scale. Learning at scale.
There you go. It's what YouTube recommended.
Yeah.
Awesome.
Well, there's a lot to this topic. I know when I first looked at DynamoDB, I thought this thing is really pretty lame because I can't get the data out the way I want. Because those access patterns that he is describing are not obvious when you first look at DynamoDB.
Right. Yeah,
I mean, it looks like a toy, honestly, when you first look at it.
Yeah, I'm definitely thinking back to when I had to operate a Cassandra cluster.
Mm-hmm.
And that was a pain.
Yeah.
That was some good times.
Yeah, I haven't had a chance to look at how they've modeled the data yet in the application that I've just joined, this new company, but we have a ton of data that's coming in. We've got all these sensors that are in these buildings that are sending us data in some cases once a minute across thousands of buildings. And this all has to get ingested and all goes into DynamoDB. So I imagine we're doing some pretty interesting little tricks with this stuff as well. So far I'm just doing the front end, so I'm making calls to the back end. I have access to the code that's running in the back end. I just haven't really had a chance to look through this stuff yet. Right. But at some point, it's one of my plans to understand that a little bit more. Just not because I necessarily need it for my day-to-day job, but I would just like to have an appreciation for what's going on there.
Yeah. Well, you got to know the access patterns that your database supports.
Yeah. And, well, we actually just had that over the last couple of days because I was presented with a new business requirement and we can't fulfill that right now. So they're working on changing that around. And as I understand, we were storing some of that data in Redis before as well. And little by little, they're getting data out of Redis and putting it in Dynamo instead and just keeping it all there as they learned more about Dynamo. And data modeling techniques got better.
Right.
So less and less in Redis. I think the intent is to eventually not put any of it there.
So there's the example of Dynamo not being flexible.
Well, I think it's probably more an understanding of not understanding ways to represent this data in Dynamo. Right. So
Right.
It was done with Redis and other techniques because they didn't understand how to do it in Dynamo because it wasn't, immediately obvious.
Right.
Because let's face it, I mean, that last example they gave in that video, there were a bunch of folks that were trying to get that to work, Amazon folks, until they brought that guy in or whatever the data modeling team is that Amazon has that's proficient in this stuff in Dynamo, right? That solution was not obvious, right? And they had to build that little chart, that sort of cheat sheet at the end, right? Where it's like, okay, if you want to query this is what you look up. Right. You then have to give that little thing out to the developers so that they understand the cheat sheet on how to go after the data they're looking at, which is, some people would say that that's not so cool, right? Like you ought to be able to just figure this out. Like if it was a relational database, you wouldn't need someone to tell you how to write the SQL query.
Yeah. I mean, the smarts have to be somewhere at the end of the day, right?
They do. And
you can hide complexity as much as you want, but at some point, someone has to understand the complexity.
Yeah. And I've also worked in cases where stuff was normalized so much that, I remember one project in particular where, there were so many tables involved. And we asked the DA at the time, the person who was doing the data modeling, how do we get this data? And they said, well, that data is derivable, which means it's queryable. You can get it out. And I remember a buddy of mine was looking at it. He goes, that's a little bit like saying there's gold in them thar hills. Because it's like, yeah, you can get it, but good luck, right? Now, how many tables do we have to join together? And we wound up having to denormalize a bunch of it because it not only were the queries really hard to get our head around, but the performance of the system was just not adequate. So, yep.
That's awesome.
I thought it was also the other part that was interesting in this talk, I thought, was how they're doing all of the sums and the averages and everything, where they're basically kicking it out to Lambda via Lambda streams, and then they're storing it as like a metadata table about the actual table. I thought that was an interesting approach to handle doing the things that you typically want to do with your queries.
Right. Yeah. We write it, trigger a Lambda to pull a bunch more data, put the sum back into the metadata field in the same table.
And then you just query that instead of actually calculating it.
Yeah. Right. What are we doing? Great.
But when I remember doing data warehousing that we basically pre-calculated a bunch of stuff, right? Because it was a lot more efficient at query time to just pull that pre-calculated value.
Yeah.
So would roll up a lot of data, like, okay, we had, data by SKU, by store, by week. And now I just want to know it, by retail. I want to know like all of, for this catalog number, what does Walmart have? I don't care about the individual stores, but maybe in other cases I do. Right. So I'd roll up that data at a lot of different levels. And there were, product aggregation codes and stuff like that, where we'd summarize a bunch of these similar catalog numbers together into one product aggregation code, stuff like that. Again, that was all rolled up and pre-calculated ahead of time. And then when I had to write the queries, they ran a lot faster.